Now that we've taken a look at causality, let's look at how the impulse response relates to system stability. So we'd like to be able to determine if a system is stable using the impulse response, because remember, you should be able to tell all of the system properties by just looking at the impulse response, because the output of the system is the convolution of the input signal with the impulse response. So we saw how causality relates to the impulse response, but what about stability, right? Stability, remember, a system is bounded input, bounded output, BIBO or BIBO, stable if for any input x satisfying, and this is for continuous time, x magnitude of x of t is less than b for all time, or magnitude of x of n less than b for all n for discrete time. So if the input is bounded, then the output is also bounded. So there's a b prime such that the output is always bounded by b prime, y of t for continuous time, or y of n is bounded by b prime for all n for discrete time. So remember, these are magnitudes. So the question is, how does this relate to the impulse response? We can look at the convolution for CT and DT. So we have the CT convolution here and the DT convolution here. And it's a little bit unclear. With causality, we could sort of plug in some values. But let's look at it a little bit more in detail for CT, and then the DT version is very similar. So suppose that your signal is bounded. X of t, magnitude of x of t is bounded for all t. So we want to bound the magnitude of y of t. Okay, so we can write down the magnitude of y of t. That's the magnitude of this convolution. And then what we can do is we can bring the absolute value, the magnitude, inside the integral, and we can take the magnitude of h and the magnitude of x separately, so we get the magnitude of h and the magnitude of x. We plug in the bound. This thing is less than or equal to b, so we get a b over here, and then we're looking at the integral from minus infinity to infinity of the magnitude of h of tau d tau. So a sufficient condition for magnitude of y of t to be bounded, that is, we'll know y of t is bounded if this number is finite. And that's what's called being absolutely integrable. So we have we have this condition. If this number is finite, that is, there is some b prime that it's less than, then we're going to have this total bound is going to be finite as well, so the output is also bounded. So that's what we'd hope for. So what we've shown right now is that if this condition holds, then the system is stable. But we really want to know the opposite. If the system is stable, does it mean that this condition holds? So if the system is stable, does it mean that h of tau, magnitude of h of tau, if I integrate it, is less than infinity? So we can do this using like a trick, essentially. So we're going to look at a particular input which is bounded, and we're going to show that in order for the output to be bounded, that is, in order for the system to be stable, it has to be that this number is less than infinity, that this quantity is less than infinity. And so what am I going to do? I'm going to take h star, so the conjugate of h of minus t, divided by the magnitude of h of minus t. So that seems like a little weird, but basically what I'm trying to do is I'm trying to get a magnitude squared on top and divide by a magnitude, so I get just this magnitude term on the bottom. All right. And I'm going to look at the output at time 0. So here I'm plugging in t equals 0. So this is h of tau, x of 0 minus tau d tau. And so what is x of minus tau? Well, it's equal to h star of tau divided by magnitude of h of tau. Right, so we plug that in here, and then we see that this h times h star is going to give us magnitude squared. We're dividing by magnitude, so we're going to get exactly this expression here. And so remember, if we want the system to be input-output stable, then we want this number has to be less than infinity. So we need this number to be less than infinity in order for h to be stable. So therefore, stability is equivalent to this expression here. right? So an LTI system is stable if and only if it's absolutely integrable. That is, we integrate the magnitude of the impulse response and it's finite. So you can follow exactly the same argument to prove this exact condition for the discrete case, where you have then that the sum of the magnitude of the impulse response has to be finite. So I recommend doing that. You just walk through steps, step by step, one by one, exactly the same way we proved it over here, and then you can show it for the discrete case, and that gives you some insight into why this stability condition is important. So this is great, because what it means is all we have to do is compute a number, and then it'll tell us whether the system is stable or unstable. So unlike general systems, where we have to make these kind of complicated arguments, we have to make a guess to see if it's stable or not, and then try and prove it or try and find a counterexample. And it's a lot easier when the system is LTI. So this is, chalk another point onto why we care about LTI systems, because we can verify the other system properties fairly easily. Okay, so let's do a couple examples. Okay, suppose x of t is u of t. So I should say h of t here. Suppose h of t is u of t, then we're taking this integral of this thing, and the magnitude of a u of t, magnitude of u of t is equal to just u of t. But now I'm integrating this area under this curve, and it's infinity. So the system is unstable. So this is saying the integrator. Remember, we talked about the unit step as being an integrator system. The integrator is unstable, and we saw this before. Okay. Suppose h of t is now e to the minus 2t u of t. Okay. So again, this is always positive, so taking the magnitude doesn't do anything, and we're just integrating e to the minus 2t dt, and so that integral is finite, so the system is stable. So if we take this one, which is just a box of length 4, this u of n minus u of n minus 5, this is just a finite length bounded signal, so the sum of the absolute values is just going to be 4. So this is equal to 4, which is, of course, less than infinity, so this system is stable. Now let's look at one last example, which is this double-sided decaying exponential. One-third to the absolute value of n. These are, again, all positive and summable, so the system is stable. So all these examples, I guess this signal was positive, but if it was negative, you just have to take the absolute value. And if it's complex, you have to take the magnitude. So as a try-it-yourself option, so determine whether the following LTI systems are stable or unstable using exactly the same tricks that we had before. So here we have 2 continuous time and 2 discrete time signals, and I borrowed some of these problems from the Oppenheim and Milsky book because it's full of examples and practice problems of this type. Hopefully by doing some examples yourself, you can see what a convenient way it is to use this property of LTI systems to determine system stability, especially compared to what we had to do before.